Continuing with chapter 3 on vectors. What I now want to talk about is section 3.3, which is vector arithmetic. And I want to go through it graphically as well as components. Components will be chapter 3.4. We'll go ahead and get both of these covered in this section. So if we want to look at vector arithmetic, we can approach this very algebraically. If I have a vector A and a vector B, what does it mean to add two vectors? So a vector is just a length and a direction. So let's call this A and call this B. One thing to note about vectors is you can copy them and it's still the same vector, right? Just because this is in a different location, it still has the same length and same direction, right? B is to the right and this long. This is to the right and this long. That's just a copy of B. So when we talk about adding vectors, we can use the tip to tail method, which means that I copy one of the vectors and I place it at the end of the other vector and I add them together. So then the resulting vector would be at the start of the first one to the end of the second one. And that would be A plus B. And you can see that, I've drawn that in a poor place, but you can see that we could have done B first and then A, and we would get the same sum. So it is a commutative, and it's also associative. So what would it be to define A minus B? All right, using the same vectors we have, A minus B means A plus negative B. What does it mean to be the negative of a vector? A vector has a length and a direction. So when we define minus a vector, that just means that it's the same length in the opposite direction. All right. So if I were to take minus A, if A is here, minus A then is here. So that's what minus A and minus B would look like. So if we want to take A minus B, then we would just graphically take A and add to it minus B. And our resultant vector here would be given by that. All right, so graphically, this is all great. It gives us a good idea of what we're expecting. But when we start doing things numerically and we want to find an answer, it's just not that useful. You would have to, use graph paper and be very detailed. And then you're still losing accuracy based on whatever measurements you're making and precision, especially measuring angles and stuff, right? That's difficult. So that gets us to section 3.4, which is on components. Oops, wrong color. So we already talked a little bit about components when I was talking in the coordinate system section. So we have an idea of what components are. If I have my vector A, and I have my vector B. I'm going to stick with the same two here. Then let's look at the components. So I'm going to, first, I can't have components until I have a coordinate system. Because how can I talk about how much vector A is in the direction of X if there's no X? So in this case, let's just use a standard XY rectangular coordinate system. So I'm going to use red for the component of A in the direction of X and red for the component of B in the direction of X. I'll use blue for the component of A in the direction of Y. And for B, there's no Y component. All right, so we would have to be given the direction of A somehow, right? This angle theta. So now I've got some X component of A and some, or I wrote X instead of Y. Some Y component of A and some X component of A and some X component of B, and there's no Y component because it just happens to be horizontal. All right, so the way that we talk about the direction of these are by using standard unit vectors. So our standard unit vectors in the X direction, our standard unit vector is called I. In the Y direction, our standard unit vector is called J. And in the Z direction, it's K. But I'm just going to do it two-dimension right now. But we'll make a note of this. K in the Z direction. All right, so if I want to write the vector A now, I will write it as the number AY times J plus the number AX times I hat. And the hat here on a vector means that it is a unit vector. And unit here just means length 1. So it doesn't change the length of your vector. Your component number carries all the information about the length. The unit vector carries only direction, and it is a unit length 1, so that when you multiply, it doesn't change the length. So this carries direction info only. So if we now want to write vector A, we can write it as AY times J plus AX times I, and we can write vector B as BY times J plus BX times I. Of course, we know this is 0 though for our example. And now if we want to add vector A and vector B, we can just add those together. AYJ plus AXI plus BXI. All right, so now we'll group things with common direction. And we can say AY in the J direction plus AX plus BX in the I direction. And this is how you add vectors by components. So there are a couple of ways that you can think about vectors and components. The way that I tend to think about them is as a projection. If I have a vector R here, then you can imagine the projection, like imagine light coming from over here, right? And you look at its shadow, then it would cast a shadow this long. This is the projection of R onto the y-axis. assuming these are our standard X, Y axis, and that's R. So now if we imagine light coming from here, then the projection of R onto the X axis would be its shadow here. Oops, wrong color. Need to be on blue. All right, and you may know one of these angles here. And that projection is easy to find with triangle trig. That's why in physics, we very rarely use the standard position for the angle. It just is much easier to use a triangle representation. Once you have the components of your vectors, it's easy to add them. And then when you return to, you want to report a magnitude and direction. Then you would form a new triangle. In our continuing example here, we have AY, and then we have AX plus BX as the length of this side from our components, right? So now you can find this angle phi using trig, and you can find the resultant vector length by finding the Pythagorean theorem. So the resultant vector length would be the square root of AY squared plus AX plus BX squared. I should have done this in general instead of having one where the the y component of b was 0. But this would just be AY plus BY and then squared if that was non-zero. Is there anything more I want to talk about from that section before moving on? Let me double check real quick. We talked a little bit about standard unit vectors. That was the thing I wanted to make sure that I didn't forget. We did geometric adding. I think that's everything for chapter 3. If you're not comfortable with vectors, you definitely need to get some practice before trying to do some physics with it, right? So, just draw a few triangles, throw some numbers on them, and see what you can figure out. So this is side, angle, side. So that is a fully described triangle, right? Because we know this is 90 degrees. So I could figure everything out about this. So I'm going to call this angle theta and this angle phi. So if I want to find out what's the hypotenuse, let's call it r. So r then would be the square root of the legs squared and then some. If I want to find out what phi is and what theta are, there's a couple of ways to go about that. I could find out what r is and then use sine or cosine. But I prefer to use given values so you don't introduce rounding errors. So since we have both legs, I'm going to use tangent. So now remember that the tangent is the opposite over the adjacent. So if we look at the opposite over the adjacent for theta, the opposite's 4, the adjacent 7. So theta would be the inverse tangent of 4/7. What about phi? Right? If we want to find phi, the tangent of phi is still the opposite over the adjacent, but now we're looking at from the point of view of phi. For phi, the opposite is 7 and the adjacent is 4. So then we apply an inverse trig function to both sides. That just removes it on the left. And on the right, it's now the function we're applying to this number. So if you're uncomfortable with trig, I'll post some practice sheets too, so get in a little practice.